And now we come to our final video on confidence intervals. We're now going to focus not on the population mean, but on confidence intervals for the population proportion. We're going to cover the same topics that we did in the previous video for the population mean, but we're going to basically use the setting that's appropriate for the population proportion. And what we're going to see is that this video is going to be substantially shorter because we can borrow or take over a lot of the same results for the population mean to the population proportion. And the reason why is the theory behind the confidence intervals for the population proportion rests on that same central limit theorem that the population mean did. And so before we get started, if you haven't done so already, you may want to pause the video and go ahead and download this data set. So just like before, we want to think about the issues we need to consider before we do any calculations. And the main thing we have to look at, again, is to making sure that the conditions in order to use the central limit theorem are satisfied. Of course, now we're looking at the central limit theorem applied to population proportions. And those were very similar to what we had when we did hypothesis testing. Okay, so again, the confidence interval theory is based on the central limit theorem for population proportions. And so the first condition we have to check is to make sure that we have a random sample, just like when we did hypothesis testing. However, the second condition is slightly different from what we had with hypothesis testing. You might remember that when we did hypothesis tests, we were looking at the expected number of successes and failures. When we're doing confidence intervals, we're looking at the number of successes and failures in our sample. And so just to make sure that that difference is clear, notice that for the confidence interval, I'm taking the sample proportion times the sample size for the number of successes in my sample. So this is the observed number of successes and failures in my sample. For the hypothesis test, however, I'm looking at the expected number of successes in a sample of size n. And so here I'm taking the population percentage times the sample size instead of the sample percentage. So again, a small difference, but it can be important into whether or not you actually are able to run the test. And so again, these are like the conditions that we needed to use the central limit theorem when we did hypothesis testing on pi. And again, in order to use StatCrunch, we need to make sure whether we're working with a data set or summary statistics, but I think that's generally pretty obvious. So how do confidence intervals work for population proportions? And I'm going to use a kind of hypothetical scenario. Again, I'm going to look at a 95% confidence interval, but this time it will be for pi. And I'm going to go ahead and take a version of the error barometer that you didn't look at, which is a survey in which they happened to look at Turkey in that year and asked the question, are you religious, of the individuals from Turkey that took the survey? So there's my population. And I'm going to go ahead, I have to take a random sample, and I'm going to compute the sample percentage. And in this case, we'll say it's 88%. That's what it happens to be from the data set. And what I want to do is take that sample percentage and then again put an error bar around it. The trick is that I want to find some margin of error, some error bar, so that for 95% of the sample percentages that I get, this confidence interval, this red interval here, will actually contain the value of the parameter pi. And so again, the million-dollar question is, how do we find this margin of error? Okay. To understand how we get the margin of error, and it should hopefully be kind of apparent at this point that really the margin of error is where the action is. Right? The sample percentage you just compute. It's whatever it is from the sample. There's no theory there. The thing that makes the confidence interval is really the margin of error. And what I want to do is I want to go ahead and take the results that we got from the population mean confidence interval and kind of show how they're very similar for the population proportion. So again, the center of the confidence interval for the population mean is the point estimate for mu, and that's x bar, the sample mean. In other words, if you were given a sample and you were asked for the one value that you think is the best estimate for the population mean, you'd choose the sample mean, right? In the same way, the center for the confidence interval for the population proportion is going to be the sample proportion. And again, the same logic. If you had a sample and I asked you, what value do you think would be the best approximation to the population percentage, you would use the sample percentage. So notice that for both of these confidence intervals, they're centered at the sample estimate. That's the key thing that you want to notice. Now I want to put this margin of error around my estimate. And I'm going to say that I think the true value of the population mean in this case lies somewhere in this red interval. So it could be any one of these values in here. In exactly the same way, I put an error bar around my sample estimate. And in the same way, I'm going to say that I think the parameter of interest, which in this case is pi, could take on any of these values. I think it's somewhere in here. What's really interesting is when we look at the expression for the margin of error. The margin of error is always the critical value times the standard deviation of the estimate. So in the case for the population mean, our estimate is x bar. And we used this approximate version of the central limit theorem, right? To say that when we don't have the population standard deviation, we could use the sample standard deviation, and that's good enough. Exactly the same way for the population proportion, the margin of error will be equal to the critical value times the standard deviation of the estimator, which in this case is the sample percentage. Notice that the critical value is exactly the same. The critical value has nothing to do with the estimator. It depends only on the sample size and the confidence level, which is the same no matter whether I'm looking at a population mean or a population percentage. And again, we know from our talks about the distribution of the sample percentages that the standard deviation of the sample percentages looks like this. With, again, this difference being that just like we didn't know the population standard deviation, so we put in the sample standard deviation, in the same way, you probably remember this formula as having pi in here, the population proportion. Of course, we don't know that, so again, what do? We use the same sort of logic. We go ahead and we insert the sample estimator, which in this case will be the sample percentage. So notice how similar these two formulas are. And if you went through that exact same argument that I did for the population mean to get this margin of error, you would see it's identical to what we would get for the same sort of argument we would use for the confidence interval for pi. It's the same sort of logic. We're measuring how many standard deviations is going to contain a certain level of confidence, and that number of standard deviations is computed the same way, and the standard deviation for the estimator is given by this. Okay, good. So now we're going to get into how we would actually use StatCrunch to compute some confidence intervals. And what I'm going to do is I'm going to use this data set that you imported, which contains the responses from a random sample of 1,200 Turkish people on whether or not they were religious. And I want to compute a 98% confidence interval for the population proportion. All the conditions are met. I don't have to assume it, okay, because the sample is told to be random and the sample size is clearly satisfied. I should test that, but if you look at the data set, you'll see that there's at least 10 people that are and 10 people that aren't. And I'm going to go ahead and compute the margin of error. So what you're going to do is you're going to go into StatCrunch, and you're going to go to Stat, and now you're not going to go to Z-stats or T-stats. That corresponds to a quantitative variable. You're going to go to proportion stats, since you're working with a categorical. You'll then choose one sample, and we're working with a data set. So you're going to go ahead and click with data. And when you do, a new window will open up, and you're going to go ahead and you're going to fill in several fields. First, you're going to click on the categorical variable you're interested in, which is the response to the question. You have to tell StatCrunch the value for what you consider a success. So in this case, I'm interested in the percentage of people who are. So success is when I come across an individual where I see a yes. That's what I'm looking for. They're in my category of interest. And finally, I'm going to put in the value for the confidence level, which is 98%. So I go ahead and type in 0.98. And I hit compute. And we get output that is actually very similar to what we saw for the confidence interval with the population mean. And we're interested in those same two values, the lower limit of the confidence interval and the upper limit. And so we see that the 98% confidence interval for the population proportion is 85.8% to 90.2%. And if we translate that into the context of this problem, we would say that we are 98% confident that the true percentage of Turks who are religious is between 85.8% and 90.2%. Okay. So what I want you to do now is I want you to download the file Colgate. We actually used this before, so if you're in StatCrunch, you can go to My Data. It should be there. But if not, you can go ahead and click on this hyperlink, and that will also get you the data set. And you remember that was the data set where we looked at a number of dentists, and we wanted to see whether or not they would recommend Colgate along with other brands. And so what I want you to do is I want you to compute the 99% confidence interval for this percentage of all dentists that would recommend Colgate brand toothpaste, find the margin of error, and find the sample percentage. So you can go ahead and start on that now. Now, sometimes, well, I shouldn't say sometimes, but very often, you're not given a data set, but the summary statistics. And I made that change there because when you read research papers, you're almost always given the summary statistics. So let's go ahead and see how that would work. So let's suppose that we're told that a random sample of American adults was taken, and we find that 80% of them think that politics has become too polarized. And let's assume again that our sample size is 1,200. Okay. So I want to go ahead and use this information to compute a 90% confidence interval for the percentage of all Americans who think politics has become too polarized, and find the confidence interval and find that margin of error. So how do we do that in StatCrunch? So now we do something a little different. What we do is we again choose proportion stats, one sample, but now we choose with summary. And one thing that's a little different that makes this problem a little trickier is you have to enter the number of successes. So here what you're going to do is use your sample size, which is 1,200, and multiply it times the sample percentage, which was 80%. And if you do that, you'll find out there are 960 successes. Now I can clearly see that the assumptions are satisfied. I have more than 10 successes, and if you look at the complement, which is the number of failures, it's going to be 240. So I've clearly satisfied the assumptions. I'm going to go ahead and put in the confidence level, which was 90%, right? And hit compute. And again, there's my confidence interval limit values. So my 90% confidence interval for pi here is between 78.1 and 81.9. And again, if we translated that in the context of our problem, we would say that we're 90% confident that the percentage of all Americans who think politics is too polarized is between 78.1% and 81.9%. Okay, good. And so let me just show you this in StatCrunch. I'll go ahead and I will run through this in StatCrunch. So proportion stats, one sample with summary, 960. And you might have to do that calculation off to the side depending on what the percentage and the sample size is. Sometimes you can do it in your head. Okay, there's your sample size. Okay. I am computing a confidence interval, and my confidence level is 90%. And as advertised, there we go. And I've already done it here, so that the output's here twice, okay? Very good. So what I want you to do now is to go ahead and compute the confidence interval for this problem. So Pew Research reports that in the sample of 1,398 people who had been married previously, it turns out that 48% of them said they had had a divorce. So I want you to go ahead in StatCrunch and compute a 90% confidence interval for the percentage of all married people who have had a divorce. So we want to figure out what is the margin of error and what is the confidence interval. So you can go ahead and do that reading quiz now. Okay, the last thing we want to do is we want to go back, and just like we did for the confidence intervals and the population mean, we want to think about how the sample size and the confidence levels affect the confidence interval. And it turns out that it's exactly the same as it was for the confidence interval for mu. Okay? It turns out that as the confidence level increases, the margin of error increases. And this shouldn't be any surprise, because if we go back and look at the expressions for the margin of error for the confidence intervals for both pi and mu, we see that they have the same critical value, and this is where the confidence level comes in. So we said before, as the confidence level increases, what happens? That area in the middle of the sampling distribution for the estimator increases. Those critical values get pushed out, so the number of standard deviations is going to increase. So now again, we think about the standard deviation as a unit of measurement. So this means that we're going to have more standard deviations in our margin of error as the confidence level increases. And the same thing is true for the sample size dependence. As the sample size increases, the standard deviation goes down in both cases, and that shrinks the margin of error. And this should be relatively common sense by now. It should make sense to you that as the sample size goes up, our estimates are becoming more precise. So our error bar that we're having to put around our estimate that we think captures the population parameter should be also shrinking. So again, the margin of error is a measure of how precise our estimates are. And we know larger sample sizes, more precise estimates, less error on average, error bar decreases, margin of error decreases, confidence intervals get smaller. And hopefully now that train of thought, that argument, that kind of train of logic there should be pretty self-evident to you. And again, as the confidence level increases to be more confident we contain the parameter value, we have to make the margin of error bigger, and the confidence interval gets bigger also. Okay, I hope that has helped, and you are totally ready to do the homework now. If you have any questions, of course, feel free to let me know. Thank you very much.